Let's make a start, everybody. My name is David Steinberg, and I'm director of the Edinburgh Business School Graduate Apprenticeship Programs. Before I introduce my very special guest today, I want to welcome everyone to week 4 of my graduate apprenticeship course called Business Skills for the Second Machine Age. I know we have a wide audience today that includes GA students from across Heriot University, GA client organizations from public, private, and third sector organizations, and members of Heriot Women in STEM and Women in Engineering. I'd like to ask Professor Heather McGregor, Executive Dean at the Edinburgh Business School at Heriot University, to say a few words before we begin. Heather?
So welcome everybody, and particularly Jennifer, I'd like to say a personal, very warm welcome to you. We are incredibly grateful that you are speaking with us this afternoon. We're all tremendously excited to hear what you have to say, and we know it will be very inspiring as ever. I will now pass back to David to do a formal introduction, but I just wanted to tell you that you are very warmly welcomed.
Thank you, Professor McGregor, and I'm pleased to introduce Jennifer Harris Trosper. Ms. Trosper is project manager for NASA's Mars 2020 Perseverance rover. In the 30 years since her initial hiring at the Jet Propulsion Laboratory, Ms. Trosper has held critical engineering leadership roles on every spacecraft ever to have roved the surface of Mars. Ms. Trosper joined the Perseverance team in 2015 and held several leadership roles during the development and operations of the mission. Initially as the mission system development manager and surface phase lead, she worked with her team to envision and design the rover's onboard autonomous capabilities and state-of-the-art ground system necessary to meet the challenging science objectives of the surface mission. Ms. Trosper then transitioned to the role of the project system engineer and engineering technical authority. In that role, she led the project-wide systems engineering teams, verification and validation program, and technical risk assessment for the launch, cruise, entry, descent, and landing and surface capabilities during the integration and test phase of the project's development. Shortly before launch, she transitioned to Mars 2020 Deputy Project Manager, leading surface development and supporting the oversight of cruise operations and EDL verification activities. She's now the project manager and leads the Perseverance team and rover project to acquire a scientifically valuable and diverse sample cache for future return to Earth. Ms. Trosper holds a bachelor's in aerospace engineering from Massachusetts Institute of Technology and a Master of Science degree also in aerospace engineering from the University of Southern California. Raised on a farm in Ohio, inspired by her father's stories of rocket launches he saw as a member of the U.S. Army Corps of Engineers, Ms. Trosper, together with her husband, U.S. Air Force Lieutenant Colonel retired Randy Trosper, now raises 3 children in Southern California. Jennifer, thank you for spending some time with us today. The virtual podium is now yours.
All right, thank you, David. It's great to be here with all of you, and I have to say, when I listen to the introduction, it sounds like I can't actually hold a job, but that's not true. We change jobs a lot at JPL as we go through the different aspects of the mission. And so I've been on all these rovers. I want to start a little bit here, just to, let me get my screen sharing going so I can get my slides sharing. What I'm going to do today is tell you, let me get this to screen mode, tell you about our mission and our team and our vehicles. The talk is about the teams, but in order to understand our teams, you really have to understand our missions. And so I'm gonna talk to you guys about that. So it's really an honor to be here. Thanks, David, for inviting me. As you mentioned, I'm currently the project manager of the Mars 2020 Perseverance rover, which you see in this image here. This is about a year ago, February 18th of 2021, we landed Perseverance on the surface of Mars. This is a picture that we took while we were landing the rover. First time ever done, and I have to say it's still one of my favorite pictures, have poster on my wall, and it's pretty cool. And this, I think, was something that it didn't just, it inspired everybody who looked at it, including our team. We were just amazed at what had happened. And since then, in the last year, we've collected 7 samples of rocks on Mars that will be eventually returned to Earth, and I'll talk to you about that a little bit more. But before I get into that, I want to talk about our family portrait. So our teams include, we are families, and our families include autonomous vehicles. I have worked on all of these vehicles in different capacities for my career, and what you can see in the upper left-hand corner is the Sojourner rover. The Sojourner rover was the very first rover we sent in the late 90s. It was attached to a lander. And it's about the size of a microwave oven, and it could only go about 100 meters from the lander, and we had to communicate through the lander. But that rover, what we were trying to figure out at that point was just how to land on Mars. We used these big airbags and it bounced across the surface. It was crazy. We don't do that anymore. We do a more controlled landing, as you'll see. And we were also trying to understand whether Mars had ever had water. There are lots of different theories about Mars, but as we got to getting to the surface, we started to understand more things. And Sojourner, that rover, really transitioned the whole way that we do Mars exploration, from landers that can only get to a certain spot or orbiters that are high above the surface to actually being able to be a roving geologist on the surface of Mars. And then in the upper right are Mars exploration rovers. Let's see if I can get, there's a little video that runs with this, but I'm having trouble getting that going. Let's see if it runs. I think, yeah, it shows all of them driving. So the Mars exploration rovers were Spirit and Opportunity, twin rovers we sent two because we wanted at least one to work. We know that Mars is hard. Those rovers lived a long time. We designed them for 90 days, and Opportunity lived over a decade. And they actually did determine that water had once flowed on the surface of Mars. But what we didn't know was whether that water was any sort of water that could have sustained any form of microbial life. And so then in the lower left, you see the Curiosity rover. Curiosity was our first big rover, the size of a mini car, very much an enlarged vehicle. We stopped using the solar panels. We used a radioisotope thermoelectric generator. So we had kind of a plutonium power source, and you can see we could drive lots more places with those large wheels. And then we started putting large robotic arms on it. And Curiosity rover actually discovered, based on a chemical lab that it had in the front of the rover, that Mars had habitable environments, meaning it had the building blocks of life. The water had been fresh in the past. And so if life were to have formed there, it would have been sustained at that level. So then Perseverance rover is in the lower right, and we saw that drive past. It looks a lot like Curiosity, you'll see. But one thing we do have is a whole new sampling system. And our job on Perseverance is to go and search for signs of ancient microbial life on Mars, because that's the next step in this rover family portrait. So next, you'll see something I like to call our vacation photos. So we like to have fun. Our rovers like to have fun. And you can see in the background there, a helicopter called Ingenuity that we took with us, actually under the belly of the rover. So these are some vacation photos that we've taken on Mars. There are selfies. The way we take a selfie is there's a robotic arm on the front of the rover, which you actually can't see in this image. And it moves all around and does this selfie. What you see in the image that's inset is that robotic arm, and it has a camera on it, and all the different locations it has to go to in order to get this beautiful selfie image. So this is a selfie of us taking a selfie on Mars. And that's how we have fun in the engineering world. Okay, so why are we going to Mars? Let me give you a little bit more context on the science, because again, that helps you understand our teams, where scientists and engineers have to cooperate together in a way that is not, is not done in many missions. Because there's so much engineering complexity and there's so many interesting science questions. So what you see on the left here is a possible Martian past, and that looks a lot more like Earth. On the right, you see Mars today. So I talked about how we know that Mars used to have water. We don't know what happened to that water. We think in order to have water, it had to have a thicker atmosphere. We don't know what happened to that atmosphere. So we're trying to understand how we got from the past to the present of Mars. And one of those things that might help us understand that is whether Mars ever had microbial life. But how do you even get to answering the questions about what happened to make Mars that way? Well, it's sort of like your realtor tells you, at least here in LA, location, location, location. So we chose a landing site on Mars called Jezero Crater. And here you see an artist's depiction of what we think Jezero Crater looked like in the past. And so in the upper left, you can see a river inflow channel. Then you see an ancient lake. And then on the right side, you'll see the outflow channel. Now at the inflow channel, at the top of that ancient lake, currently we see a delta. So what happens on Earth and what looks like happened also on Mars is when these rivers flow, they bring a lot of sediments and they deposit them right at that inflow. And on Earth, that is the place that has the greatest potential for preservation of any sort of life that was in that river or that lake. And so that's why we went to Jezero Crater, and that's why we're looking there. The Jezero Crater doesn't look like that today. It looks like this, as I mentioned, I mean, it dried up. Mars dried up, the atmosphere went away. And so this is what it looks like. If you look really carefully up here in the inflow, you'll see something, and I'll show some more closer up pictures. This is the delta in this upper left where the inflow is that we're very interested in. At the base of that delta is where we want to get some samples. And so we chose to land at that part of the crater. We landed a little bit away from that, which I'll talk about. And then the other thing we have to do is figure out, well, how are we going to explore this? Where are we going to go? What are we going to take with us? This is our rover. It has a number of really fascinating scientific instruments. On the right side, you'll see this robotic arm, which has a huge turret. It has two really critical instruments for us. One is called Pixel. It's an X-ray spectrometer. That gives us millimeter scale and elemental composition of the things we're looking at. And then Sherlock is another millimeter scale and carbon measuring spectrometer. So those are, once we use our other instruments, like the SuperCam, which is we have a microscopic imager, so it's like a telescope, we can see very far away, and our mass cam that are on the mass to choose and select our targets. These instruments, Sherlock and Pixel, can get millimeter scale information about them. Meta is our wind sensor, and it also gives us temperature to weather sensor. And then RIMFAX is a radar that was that is actually looking at the subsurface, trying to understand how the different geologic units relate to each other. And then we have some technology demos. So in addition to all of the, go and find evidence of past microbial life, the team was also asked to do two technology demonstrations. The first one is called MOXIE, and there's a picture of the instrument here on the left and a hopeful future on the right, where this instrument is actually designed, the Martian atmosphere is largely carbon dioxide. And this instrument is designed to use a solid oxide electrolysis process to take the oxygen out of the carbon dioxide atmosphere. Why do we want to do that? Well, if we want to send people there, or if we want to send rockets there, we need fuel for the rockets and we need oxygen for the people. And so we've been able to demonstrate this successfully. We get about 5 grams of oxygen every time we do this, which isn't a lot. But the team that built this is already scaling it at MIT to make it a much larger instrument for use on a future mission. So this has been a huge success. The atmosphere on Mars changes through the seasons. So we do these experiments regularly to understand, as the atmosphere changes, what different parameters we have to use to get that oxygen out of the atmosphere. And the other technology demonstration that we have executed is the helicopter, which is just a super fun little guy named Ingenuity, or gal. You can see it was placed, the rover's upside down in this picture in the upper left. And the helicopter was folded up underneath the belly of the rover. It was kind of a late ad. There was a lot of discussion of are we not going to fly the helicopter? So as we were building the rover, we continued to try to accommodate it. But you can see there's a lot of complexity to that accommodation. In the upper right, you can see the helicopter was folded over. And then you can see once we deployed it on the surface of Mars, it took us about a week and a half to just unfold it, drop it, and then drive away so it could get solar array, it could get sun on its solar panels there that you see on the top. And I'll show you a neat. So now I'm going to pause for a minute and say, those are the types of missions our teams build, and they've definitely evolved over the course of my career. The Pathfinder mission was much simpler than what we're trying to do with Perseverance. But in these missions, there's some very unique challenge that NASA missions have, and also these Mars rover missions kind of have in spades. And I wanted to talk about those because those define the kinds of teams and the things that the teams need to value. So as you can see, the mission objectives, they're broad, complicated, and typically include many firsts. Go to Mars, find evidence of microbial life, and by the way, fly a helicopter and get some oxygen out of the atmosphere. Big mission objectives. The second thing that is really challenging is the significant constraints that we have. The launch vehicles only take so much mass. We actually only know how to land so much mass on the surface. We can only have so much volume. We can only have so much power and energy. And because of that, instead of having a nice system like an aircraft carrier that you decompose and everybody builds their own piece and delivers it and plugs it into the next thing, but they can make sure it all works before they give it to you, our systems are highly coupled, and I'll talk to you about that. But there's one motor controller for everything on the vehicle. And so that motor controller has to be able to move the mast, it has to be able to move the robotic arm, it has to be able to move our sampling caching arm that's inside the rover. There's a lot of coupling that makes us build our teams a certain way. And the other thing is the cost and schedule pressure. Everybody has cost and schedule pressure. Our schedules actually are dictated by orbital mechanics. And so every 26 months, we have an opportunity to launch something to Mars based on our current launch capability. And if you miss your 30-day launch window, you wait another 26 months. So it's a different kind of schedule pressure than a lot of people feel. And that's why we work in a certain way as well. And then, of course, our robots are unmanned or unwomaned or unpersoned. And so they have to be very autonomous and they have to keep themselves safe. So those types of things make the team have a challenge of this complex thing that they need to build. So how do these teams really succeed? And so I've put this, a lot of times we talk about this at JPL, is what is the secret sauce? What is the secret sauce that makes these things work when they work? And I've kind of captured it in two areas. And some of these things are probably, no-brainers, and some of them you might be surprised. But the first one I'm going to talk about is a set of team characteristics. And then I'm going to talk a little bit more about the mission. And then I'm going to tell you some things that we can do as leaders to help your teams not get stuck, because and to solve problems, because a lot of the challenges of these missions are really just getting the teams to move forward once you form those teams. So let's talk about the team characteristics just for a minute. I would say the coin of the realm at the Jet Propulsion Laboratory for these teams is technical excellence. We talk about technical excellence all the time. We demand that, insist that in our people. And if they don't have it, we challenge them on it. And that's what critical technical review is. It's sort of like, I was taking my kid to his conditioning for his baseball team last night. And I thought, technical reviews for us are sort of like conditioning for a sports team. You prepare for it, you get ready, you make sure that your design is solid, that you've understood the verification program, that you've done the math right, that the physics aligns up. And then you go and you talk about it for a couple hours in front of a group of people who know a lot about a lot of different things. And by the time you get to the end of that, you may feel good, you may feel bad, but you've had a great technical review. And that's really what we focus on. And so, and then the other thing is the out of the box thinking. In order to do missions like this, we just really need to encourage people for that. Sometimes, NASA can be considered, people think we're a bureaucracy, but at JPL, we have to do things the first time, like the helicopter. And so you got to think out of the box. In fact, my husband, who was a test pilot in the Air Force, he was like, he said, Mars doesn't have an atmosphere. It's like 1/100th of Earth's atmosphere. So I don't think the helicopter is going to fly. And so you had to have people who are thinking, yeah, but he's a jet pilot. So of course that's what he would say. But the helicopter flew and it's still flying. That's pretty amazing. Team-oriented vision. So the next thing is we are all, and I'm sure all of you guys are used to this, everybody is exceptional on the teams that we work with. And sometimes it's hard for those people to recognize that it's not just about them. But when you look at the missions we do and you see the complexity and the breadth of them, I think even people who are, very, very capable understand that they can't do it themselves. And that if the person next to them doesn't succeed, then none of us are going to succeed. And I use that a lot with my teams. We all have to succeed. If somebody doesn't succeed, then it's a problem. The other thing is we have lots of disagreements, and we allow those. It's good to have those discussions. It's good to make sure that everybody's viewpoint is heard, but then we have to align on key mission objectives and move forward. And so that's, I think, another thing that leadership can help with. I talked about understanding the need to sacrifice for the sake of the team. And then another one is really just building the team. The more I get into my career, the more I realize the building of the team is so essential. You need to understand your people and you need to understand what your team needs to do. And then you have to match those things together. And for me, sometimes that means changing the team structure. Sometimes it means changing the people. Sometimes it means getting rid of people who don't fit. Everybody has a place, but I would say sometimes it's not on your team, maybe it's on a different team. So just trying to make sure that you have the right people set up to do the job. And then the adherence to values that foster success. I'm not going to spend a lot of time on these, but for us, we have to be honest with each other. We have to cooperate. We have to communicate clearly and constantly. We do encourage a diversity of background and expertise. And of course, I have to add, you need to have ingenuity and perseverance, both literally and also as characteristics. And then the final thing I'm going to share here about the characteristics of the team before I move on to more about the mission is the strong and empowered management team. And this is something that, you know, we don't have just managers. We have managers who are leaders who have technical acumen. And that really helps our teams when we get into troublesome areas move forward. They adhere to the values that foster success, but and they're amazing people. They are just so capable, but they have to put their egos in check for the good of the team as we try to move this team forward. And again, we allow for fierce debate, but we eventually, and that is why it's so important for us to have leaders and managers with technical acumen. We have to make decisions to move forward. And all of our managers get it, our leaders, the buck stops here with them. They take responsibility. And, you know, and if they don't, we adjust the teams, but these are really important for the types of teams that we run. Okay, so the next thing is a video, and you can, the music is kind of nice, so I'll leave it there. And this shows once we actually figure out what we're designing, we have to build the pieces, and then we put it together in an assembly, test, and launch operations process, which you're seeing pieces of here. That's our cruise stage. We also have, 6 or 7 different versions of the vehicle. We run a bunch of test beds, but this is the flight vehicle being built. Here we're in an environmental test chamber where we call it shake and bake, where we heat it and cool it to the temperatures it'll see on Mars. And we also put it on a table and shake it. Those are the wheels being manufactured there at JPL. And here we are putting the mobility system on the rover. An interesting thing about, and we do it in a clean room. Obviously, we don't want to discover life on Mars that we took with us in some sort of microbe that was on the vehicle. So we all wear the clean room white suits, and we swab the vehicle all the time. This is the cleanest thing we've ever sent anywhere. Now, you see that big robotic arm and that huge turret there. That turret on Perseverance weighs 3 times as much as the Sojourner rover. And so I like to, when you talk about how we've moved through the years, Percy's arm can carry 3 Sojourners. So it's pretty incredible the advances we've made. And then here you can see we did manage to, I'll talk a little bit about COVID and answering one of the questions. COVID hit in March of 2020, and our launch was July of 2020. We were fortunate that we were at the launch site in Florida, and we, you know, adhered to COVID protocols and got the vehicle on the launch vehicle. But the other problem was back here in California, we still had a ton of work to do on the software for landing and the surface and our test beds. And so we were trying to figure out how to do that in a COVID environment. So that was very, very challenging. But we made our launch, and that is the last 2 Mars missions. One was a rover, Curiosity rover, and one was a discovery mission called InSight. They had both missed their launch window and had to wait that 26 months. So there was a lot of pressure on us to make it. In fact, that's why we're called Mars 2020 Perseverance rover, because Mars 2020 had to be in the name in order for us to make sure that that was one of the reasons we were continued to call the Mars 2020 rover. So we got a launch, and then 7 months later, we end up at the atmospheric entry point at Mars. I won't go through all the details of this, but it shows you kind of the main points of entry, descent, and landing once the way that we do it, which is a ballistic entry. The Chinese, and we've done this before, they actually go into orbit around Mars. That's how they did their last rover landing. We did that with Vikings. In this case, we do a ballistic entry. And so you can see the first thing we do is get rid of our cruise stage, and then we have this entry vehicle. The parachute will deploy. We drop off our heat shield, and that's so we can see the ground with our radar and cameras. And then you see the descent stage pops away from the parachute and the back shell. The descent stage has engines that slow us down even more. And then that's where we did our terrain relative navigation, which I'll talk about. And then it drops the rover down on these cables and gently places it on the surface of Mars. And so the image I showed at the beginning of the presentation happened right before the rover was set down on the surface. Something new we did, it's really another technology that we added If you go back to Mars Pathfinder, our landing ellipses were huge, and we're trying to get to, and the other thing is that the places on Mars that the scientists are most interested in are always the most dangerous places to land. They have rocks, they have canyons. And so what terrain relative navigation did is we took a bunch of photos from our orbiters that are orbiting Mars, and we put them on our vehicle. And then we took pictures as we were descending through the atmosphere, and we matched to the map, figured out where we were. And then if we were near a hazard, we diverted away from that hazard. And that allowed us to land in a place that had hazards. We had about enough fuel for about 100-meter divert capability. And we did divert. And I'll show you that in the next video, which is, this one gives you a little bit of a sense of our team too. This is landing day. Last February, I'm back there under the flag. This is, it's interesting. I've worked on this mission since 2015, and there aren't that many, these are days that have to work. And I remember driving into work that morning, I thought, wow, there's just no other way to do it, but I wish there was a way to do it that wasn't quite so nerve-wracking. We've done this 5 times and it's still as nerve-wracking. And the other thing that happened was early on, we had these tones that come back from our X-band, and they tell us things like all is well, or we had a fault. The very first tone that came back was a fault tone. And we didn't, and we were like, I remember thinking in my head, I'm like, oh, okay, maybe this is the one that doesn't work. And as things went on, we realized it was a little bit of a ghost tone, but it certainly, set me for a little bit of a even more nerve-wracking landing.
In preparation for parachute deploy and to roll over to give the radar a better look at the ground.
I'm going to talk about the orange and the white later. Notice how the parachute is designed.
We're seeing significant deceleration in the velocity. Our current velocity is 408 meters per second at an altitude of about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Nav filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface.
Radar lock's a big deal. You see the delta in the right side of the image.
Perseverance is continuing to descend on the parachute. We are submitting upon the initialization of terrain relative navigation and subsequently the landing engine. The current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
You'll see a sand field in the middle of the image towards the bottom. That is what we diverted away from.
Confirmation that the lander vision system has produced a valid solution in part of terrain relative navigation.
Landing.
We have timing of the landing engine.
Shell set.
Velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. With confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about 1 kilometer off the surface of Mars.
Here in safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We started our constant velocity accordion, which means we are conducting the sky crane, conduct the sky crane maneuver. Sky crane maneuver has started. About 20 meters off the surface.
Getting signals from our Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life.
It still makes me nervous to watch that. Just gonna get a little bit on edge. Okay, so we landed safely. And that, is huge, but that was only the beginning of everything we needed to do. That was sort of, it just had to happen. Now we were going to start getting samples. And this is an image, one of the first images we took. If you remember, I showed you the orbital view. Now you can see from the ground view or roving geologist view, the inlet canyon where the river came in, the crater rim. So we're inside the crater. Sita is this sand field. So Sita is in the middle of, not in the middle of Jezero, but is a little bit from the edge of the delta. And because we were coming in a little bit long on entry, descent, and landing, we maneuvered and went to the other side of Sita. And that's what our terrain relative navigation did. I'll show you another image that helps you see that. And so we're actually on the other side of the sand field from the delta. But it's great because we've been exploring a much older region of the crater, and we found things that the scientists did not anticipate. We thought this whole thing was sedimentary rock. We found all igneous rocks in the area that we're in. We could see that they were highly altered by water after they were there. We thought the olivine signature was that it was sedimentary and it was igneous. So the scientists are rewriting the books. And so that makes you know that it's an exciting and useful mission. So another fun thing that we've been up to, and I know that you have probably seen some of these, but we landed, and one of the first things we did is fly the helicopter, probably a few months into the mission. We wanted to get the helicopter flown before it had to go. You can see it coming across the image there. It's not big. It's it's about this tall, but the wingspan is pretty large. The wings, it turns at 2,500 RPMs for the rotors. And you can see there, it goes up to about 10 meters, and then it comes back down and lands on the surface. So we've been, the helicopter was intended to have 5 flights, and we tested that rotor speed to 2,500 RPM on Earth. But because it's lasted so long and the atmosphere is changing on Mars, we've been continuing to fly it, but we're actually spinning the rotors at about 2,700 RPM right now, because the atmosphere is even thinner than it was when we landed, and it's still doing well. We had an unexpected dust storm in January that it put some dust on the helicopter. So we're having to kind of clean out not just the solar panels, but some of the actuators and spin the rotors a little. But we're getting close to doing our 19th flight 19. So it's very exciting to have that tech demo coming along. And it's actually doing a lot of scouting, helping look for the rover in advance and helping the science team decide where the best places to go are. So now the most significant upgrade we made, we actually tried to use a lot of the Curiosity. We used the landing system, we added the terrain relative navigation, but there was one piece that we just couldn't use Curiosity, and this is this whole sample caching system. We had to build a whole new sample caching system because Curiosity didn't do it. So what you see here in the right side of the image is what we call the adaptive caching assembly that actually sits, it's in the front of the rover, and this, you would be looking up and you could see kind of this view if you were lying down under the rover. And then you see a sample tube there on the left, and you can see our samples are about 1 centimeter across, a little bit bigger, and then they can be up to 6 centimeters long. We've gotten different sized samples based on the rocks that we've sampled from so far, from 0 all the way up to about 5.5 centimeters long. I'll tell you about the 0. And there's another arm inside the rover that manipulates those tubes. And I have a nice little video here that shows you how it works, just because I think sometimes it's not obvious unless you see it. So here, the robotic arm, once we use all of our remote sensing instruments to choose a target, so we have our target rock, the robotic arm will place the corer. So the corer has 2 stabilizers that you see there, and then the corer is in the middle, but inside the coring bit is a tube. We've already placed a tube in there. So the sample is actually going into the tube, and we bring it out. We kind of close off the bottom a little bit. We bring it back, and then we have something here which we call the bit carousel. You can see there's some docking alignment mechanisms, and then that white thing takes the bit with the tube inside of it, rotates it around to the bottom to that adaptive caching assembly that I just showed you a picture of. It's in the bottom. And this other robotic arm called the sample handling arm manipulates the tube. It takes the tube out of the bit, it moves it into the different stations. The first thing we'll do is we'll take a volume measurement. So we stick a probe in there to see how much is actually in the tube, and we'll take a picture of the core and the tube, and then we'll seal off the tube. And the intent here, because we had so many samples, we have 43 tubes, and we want to put samples in 36 of them because we have some other, we do witness tubes and regolith and things like that. But that is a very ambitious timeline. So our intent of the design here, and you can see putting the tube back in storage, the intent of the design was to be able to do that whole thing in a single sol on Mars. So it's very autonomous. And we've done that several times. We've also put the ground in the loop a couple times because of a problem that we had on our first sample. So our first sample attempt was back in August. And what you see here in the upper middle, before we do a sample, we'll always we take an abrading bit, which is a different bit, and we just dig into the rock a little bit and put our instruments on there to see if it's worth sampling. So what you see is the abraded patch in that upper middle location. And you can see there were some holes here, but when we looked at this, we cored a ton of rocks on Earth, dozens and dozens of rocks on Earth. We thought this looked in family. The scientists thought it looked in family with what we've done. You can see here in the upper right, you can see the abraded patch, and then you can see this borehole. And the borehole looks normal. In fact, I remember this is our first sample. So this was a big deal. It was 2 a.m. when these images came down, and we all got on the WebEx and we saw that there was a perfect borehole, and we were very excited because we expected then those next steps, and we had never on Earth gotten a perfect borehole and not gotten a sample. So we just kind of assumed everything else was going to happen correctly. We came in at 8 a.m. when we were getting the next images. And I remember the chief engineer for the sampling system, I happened to be a friend of hers from MIT, and we were sitting in the room together and we saw the sealed tube. And we were, and I could just see, just see the stress and the relief kind of rolling off of her and me, and we're like this. And then we see this image that you see in the bottom middle where the tube is totally empty. And so we sealed an empty tube. And then we're like, oh man, how did that happen? As we often do, because we have so much experience with solving problems and things not going quite the way we wanted them to, we took our hands out of the air and we, got our computers and pencils, and we actually sequenced an image that you can see there on the lower right to try to figure out where the bottom of the hole was to see if we had dropped the sample in the hole. We looked all around the rover. And if you look in the lower left, there you can see that there isn't a sample in the tube, in the bit, in that image. And so what we over time discovered, I think in the moment we had to decide whether we were going to try this again. And because the system itself appeared to work perfectly, except we didn't get a sample in the tube. The good news is we actually had a requirement for an atmospheric sample. So we seal atmosphere in this tube and it's very clean. So we checked that box with this particular thing. And then we went off to a rock that was less weathered, and we got our first samples. And you can see these two holes in the rock down here. This was our first pair of samples. We have paired samples because of the way our caching strategy is for the next missions that will come and bring the samples back. So we pair most samples. We take two. You can see here the difference. So here is this is an orbital image, and you can see the white up in the upper right is where we landed. We've traversed all around this sand patch, this Sita sand patch, and I'll use this one because it's a little bit better. You can see all our traverses. Green is where the helicopter currently is. Down here in the lower part, you could see is where our first sample attempt was, and then we came all the way up and drove into this region called Sita and got the rest of our samples that we've gotten. And then you can see where this is on the left side of the image with respect to the delta. So soon we're going to be driving back to our landing site and up around the sand dunes to get back to the delta. And then here you can see the different samples that we've gotten. They're all igneous rocks. They're all very weathered, and they have lots of big grains in them. And our Sherlock instrument has even found organic. So it's exciting. I'll point you to, we have a lot of science papers coming out soon, and a lot of them out that talk more about what we're discovering. And then, well, what are we going to do next? Why are we doing this? So we are the first step of Mars sample return. The next step which is happening in the early 2030s, it would be when they actually arrive. There's a sample retrieval lander and a fetch rover. The fetch rover would retrieve our samples, put them on the sample retrieval lander. There's also an option where if we're still alive, we keep some samples and we directly transfer them to the sample return lander. There's an Earth return orbiter that's in orbit around Mars. This Mars ascent vehicle, once loaded with samples, takes off from the surface of Mars. And then there's a container in here that rendezvous with the Earth return orbiter, and then we bring them back to Earth. So it's exciting. It would be a great capstone of a career for somebody like me to see that happen. So I'm really excited about it. And then a possible future with humans and bases on Mars. So now let me take it back to the team and say, because I talked about some of the challenges, how do we as leaders help teams move forward and deal with challenges, and how do the teams need to behave? So I have a few things here to say. One is prioritization. I talked about the launch schedule here, and our teams often just get overwhelmed with the amount of work they have. In particular, our system engineers, we have so many interfaces, and I'll talk about that. There's so much work. So we regularly are asked by our teams and do come up with different versions of priority lists, and we have to come up with the principles for them. And sometimes they're simple, right? You have to have the hardware built and tested before you launch. You don't have to have the software for landing built and tested before you launch. You have to have that before landing. I mean, it's basic, but it drives a lot of how we manage the work. And so and the other thing we do is I'll have a 5-item priority list. And then we'll have a 90-item priority list. And when we update them, because it helps the teams. And obviously you don't do 1, 2, 3, 4, all the way through 90 in order. It just helps the teams kind of figure out when they have 40 things to do today, which 5 things they should really focus on. And that also helps us with our stakeholders, and in particular science. We'll make sure that they think we're prioritizing the work that they think is important as well. And then another thing that we do, and I have 2 slides on this, and this one is, I think, a bit of the secret sauce here, but it's necessary, right? You don't always need this secret sauce, but we do because of all the constraints that are on our systems. And I call it multidimensional and evolving team structure. But it really comes from the fact that we have so much coupling and there's so many interfaces. And I'll show you a diagram of that in a minute. But so we put system engineers and chief engineers all over the place, for lack of a better term. We structure the system engineers around the physical decomposition of the vehicle, the functional decomposition of the mission, the organizational decomposition of the implementation, and then the operational decomposition of how we do the operations. And so there are overlaps, but everybody's looking at things from a different perspective. Does this meet the function? Did I get the hardware built, and does it meet the thermal requirements and the power requirements? And then we evolve this organization over time, because you have to, because the systems arm at the beginning has to be strong and defining, and then they can be a little bit less strong and go deep into the building. But then when all the pieces come together, they have to be strong again and large in the making sure it all works when it comes together because of this coupling. And I'll just give you an example here, and I don't want you to read the words or anything, but we have many high-level functions that the mission has to do. An example is robotic arm science. Those 2 instruments, Pixel and Sherlock, have to go and do science with the robotic arm, placing them, Pixel, within a few centimeters of the surface of Mars, from Earth, by the way. And so that's the mission function. But our organizational decomposition builds the payloads separate from the flight. So the payloads, Pixel and Sherlock, separate from the flight system, the robotic arm, all the motor control that goes with that, all the flight software that goes with that, separate from the operations that has to operate it. And so I just put green dots and arrows in here. The green dots are all the places we have system engineers, and the arrows are all the places we have interfaces. And I didn't even put all the arrows in, but it just gives you a sense of why you need to think through the structure of the team and the perspective that each of the members needs to think about. And the system engineering way we do business is, I think, essential to how we can be successful. Okay. And then another one that we like to do, we all like to think about the bad things that could happen. And this, I think, helps our teams. I'm not saying we like to, but we need to. And just in general, in building things, all of our analysis and design techniques are driven by worst case. the team actively runs and regularly runs operational simulations with multiple anomalies. And it's not just because we need to understand how to solve the anomaly. We need to understand how to work together to solve the anomaly. We have our crews and EDL teams are dozens of people, and our surface teams are hundreds of people. And getting that many people to work together to solve a problem, for example, when we didn't get that first sample, we had hundreds of people going, okay, how can I help? What can I do? And so we simulate those things, and we call in people, we call them the gremlins, and we bring them in and they'll do something like simulate the rover landing on a big rock, and you tried to deploy the mast and it only went halfway. And so you have to figure out, wow, am I worried that should we drive off the rock first, or should we finish deploying the mast? But then it might, so there are all kinds of fun problems that we solve in these simulations. And then we also we encourage people in these reviews to ask questions about, what if this goes wrong? What if that goes wrong? And you can't mitigate everything, but you also need to make sure that you understand the likelihood so that you mitigate the things that you want to mitigate. And then one of my things I've learned through the years, I mean, we had an anomaly on Spirit. It's Sol 18. It was the 18th day on the surface where we thought we lost the vehicle. We could not get in touch with it. We lost communications for a week. We were trying to figure out what went on. And the interesting thing about that one is, a week after that anomaly happened, opportunity was coming to land on the surface of Mars, because they were like 3 weeks apart. And so it was a crazy time. But I think what always helps us is we have to be disciplined to work the problem. And we say this to our teams, we say it to ourselves, because you can get emotional, you can get distracted, you can be like, oh, what are we going to do? This is a multi-billion-dollar national asset and we can't talk to it. What are we going to do? But you work the problem and you work the details of the problem. And that is kind of how we make sure we make progress. And, we got out of that one. We actually figured out the software was in an infinite reset because the flash was full because of another issue. And so we eventually reformatted the flash, made sure the problem didn't happen on opportunity, and move forward. But those are definitely times that take years off my life. Okay, now back to the people a little bit more, and this is just in closing. I want to talk about the human side, not just the teams, but the people themselves, because it's all about the people. And what we have here is some festooning to recognize humans that is on the rover. In the upper right, you can see, because of COVID, we wanted to recognize the medical industry that had worked so hard during this time. And so we put the medical symbol there. On the lower right, there are 11 million people's names who wanted their names sent to Mars etched into some chips here. And then the lower left is one of my favorites. You can see the rover tracks as they are, but then the rover tracks are twisted to look like DNA, because we know that all of our rovers are of human origin, and that's what makes them who they are. And so speaking of humans, this is just a small part of the team of people who put this together, thousands and thousands of people that it takes to build and make missions like this succeed. And each one of these people is very uniquely talented. But when you put all these people together, you really can accomplish impossible things. And with that, I'll end with the parachute with the orange and the white. So I showed you this slide, and the parachute code was inspired by a quote from Theodore Roosevelt. It's a binary code of orange and white on the parachute that spells "Dare Mighty Things," and it also has the GPS coordinates of JPL, because we like everybody to know where we are. So here's the quote: "Far better is it to dare mighty things, to win glorious triumphs, even though checkered by failure, than to rank with those poor spirits who neither enjoy nor suffer much, because they live in a gray twilight that knows not victory nor defeat." So thank you for sharing these great successes with us. As we all dare mighty things together, we'll undoubtedly continue to turn the impossible into reality. Thank you very much.
Thank you very much, Jennifer. What a remarkable presentation. And just to recap, technical excellence, team-oriented, strong and empowered management team, prioritization, multidimensional and evolving team structure, preparing for the worst with your gremlins, working the problem, and the human side being the most important things. Terrific. We'd like to move to Q&A if it's okay. We've got some questions for you. Is that okay?
That's great.
Okay, great. And I think Alex will put up the questions so that everybody can see them. They've come from my class. There is one that has just come in from our chief entrepreneurial executive, David Richardson. I just want to make sure that we have a chance to have that question.
So can everyone see my screen?
Yes, we can. Alex.
Okay, I'll move on to the first question then.
Perfect. This is one that, yeah. As soon as it changes. Okay, good. So David Richardson. So in a former role, David had the pleasure of working with the late Piers Sellers, who helped us land a Valkyrie humanoid in Edinburgh. How long do you think it will be before we see a humanoid on Mars?
I think there are some steps in working the problem. And I think it's very exciting once we are able to bring these samples back. I mean, my guess would be if we have the national will and the focus, which is a lot of the importance of this, I think we have the talent and the capability to do it in the next, few decades. And I think that that would be exciting and, a great next step. I think it's interesting that you were able to work with peers, and that's pretty cool. I was not aware of that.
Okay, next question, please. Okay, in the 20th century, Jennifer, the space race involved two players, the Soviet Union and the United States. Today, the race involves many more state-sponsored space programs and now private initiatives led by entrepreneurs. From your point of view, how does the increased competition factor into the planning of new missions?
So I think there are two pieces to this one. The first one is, it's great, as a person who works at JPL and sees all this private industry starting to enter the space age and do things like, especially in the manned space program, to bring people and to bring other things into orbit. I think that's really important because we want these private companies to fill in the gaps so that places like JPL can build a Europa Clipper mission that's going to Europa. And if nobody comes in, is able to take cargo to the space station, is able to send people into low Earth orbit, then we just don't have enough in the national arena to do all the things that we want to do. So I think it's great. I am always an encouragement of the private initiatives. As far as the second piece, which is the new space race, I do think it's interesting. Back when it was the Soviet Union and the United States trying to get the first person into orbit, and then, who got to the moon first, we are trying to get samples back from Mars. We're also trying to get humans on the moon in a base, and eventually people on Mars in a base. The Chinese are, for the very first time, they're the other country that has now landed something on Mars. They landed a rover. And so they have said that they're going to bring samples back in the early 2030s, which is consistent with our plans. And so I see that as another, potential space race where as the United States and our collaborators, we have different European countries who are ESA is working with us on the sample return, that we will probably want to prioritize that in a way that, we are able to accomplish that first.
Okay, thank you. Next question. How did the COVID pandemic affect Perseverance mission operations?
It's a great question because I know that everybody out there was affected significantly by the COVID pandemic. And so nobody escaped, and Perseverance mission operations didn't escape. I'll say three things or a couple of things to that. Number one, we were fortunate it was closer to launch. So it really was the mission operations that were affected. We're used to being teams that get together and collaborate and talk to each other. And we actually think that is part of our secret sauce, is being together and having those hallway conversations. So when the pandemic happened and in the early times, you remember, I was talking to the institutional leadership about how we do our operations fully remote. And so in addition to just getting done with everything we had to get done, we're trying to re-architect the whole way we do business. And it was very challenging. And, you know, I spent half of my time doing that. I thought, oh my goodness, what am I missing that I would normally be doing, because I'm spending half of my time worrying about how we do operations in the COVID scenario. So what we ended up doing is kind of a hybrid. We had a subset of folks on lab who were following all the COVID protocols. And then we have a lot of people who are remote. And I think for me, it actually has helped change my paradigm of, and I think probably a lot of people, how remote work can work in certain situations. I do think we definitely benefited by being together and knowing each other for 5 years before we had to be remote, but we are able to be largely remote. We have 40 people on lab every day now for surface operations, and everyone else is remote of the hundreds of people. So I do think that the people are maybe more burned out, because just like me, you spend 14 hours a day on WebEx meetings, and then you walk out and you go cook dinner, and you know, get your kids do their homework. And so I think there's just, you know, it seems more intense. And so we're trying to figure out how to give the teams some breaks, but it's, yeah, we've been surprisingly successful here.
Great. Next question. A Harvard case study by Leonard and Myers includes a discussion on the need for a balance between innovation and replication of prior solutions. How did your experience with soil sampling on prior Mars rover missions factor into the design of the sampling system at Perseverance?
But this is great, because I totally agree. And I think part of what we were able to do is leverage the heritage. So we call it heritage hardware and software of a previous mission. We leveraged a lot of heritage from Curiosity. You can see how much the rovers work together. We didn't actually leverage so much of the sampling system. You can see we leveraged a robotic arm, but the sampling system itself, because it had different functions than the previous one, we largely did that from scratch. So the adaptive caching assembly and the bit carousel, but the robotic arm, and then all of our avionics, all of our launch crews and entry, descent, and landing was largely built to print, except for things we added like terrain relative navigation. So it was only because of that reliance on heritage that we were able to get and make the 2020 launch, because as I mentioned, the vehicles are complex. Now the soil sampling, the thing that we do, we always bring the people. So the people who built, as many as we still have at the lab, the people who built the Curiosity soil sampling system, this chief engineer I was talking about, she was chief engineer on Curiosity, and she's chief engineer on Perseverance for this system. And the people bring that, as if you can't bring the hardware, they bring the knowledge to make the right innovation.
Great, thank you. Next question. The name of the last rover mission to Mars, Perseverance, gives us an insight into the strength, determination, and planning that has gone into each mission. How have you seen advancements in robotics technology affect planning and development of the project over time?
Yeah, well, so since I showed you the Sojourner rover, you kind of can see the difference between the rovers. But an example is we just broke an auto navigation record yesterday. Yestersaw is what we say, because the sol is a day on Mars. So yestersaw, we drove 224 meters and autonomously, so the rover figuring itself out, making its own maps. And the previous record was held by Opportunity for 15 years at 220 or something. And so we are autonomous navigation. And then if you go back to Sojourner, it can only drive 100 meters from the lander. So we become very capable, and we want this rover to move quickly so we can spend a lot of time doing science. Another thing is pinpoint landing. Even though we had this terrain relative navigation, and basically that capability, we had a landing ellipse of 10 kilometers. It was 100 kilometers on Sojourner, and once you get to our next missions, it's essentially pinpoint 60 meters. So the way we can land on the surface. And then there's one more thing I'll mention that we're still in the process of doing, because of that whole prioritization thing. A lot of times the autonomy gets pushed to the right because the people can always do it if they have to. So one of the things that we've pushed to the right, but we're still working on with Perseverance, is an autonomous planning capability. So we are pretty conservative when we tell the rover when it needs to heat how long it takes to heat something up. A lot of what we do is making sure things are warm enough to do the job. And we also don't know necessarily how much energy it has at the end of the day, because we don't know how long it drove and things like that. So we're looking to have the rover figure that stuff out on its own versus us tell it that. We have something called Simple Planner. We're hoping to roll it out, let's see, the end of this year, so that the rover is much more autonomous in making its own decisions. If it has more energy, it keeps going. If it does another task that we told it was the next thing to do, we just didn't know if it would fit in the plan.
I'm conscious of your time. We have a few more questions, but I want to ask you whether you can take them.
I can, yeah, sure.
Okay, wonderful. Next question, please. Thank you. Please put your exobiologist hat on for just a moment. What signs of life on Mars, past or present, do you hope in your heart of hearts to find with Perseverance?
So my exobiologist hat knows what my exobiologist friends have told me. And so I would say that we took a group, and I didn't go with it, out to Australia, Western Australia, and looked at something that's called a stromatolite. And a stromatolite is what happens when you have microbes growing in lakes and sediments. And so it is a clear signature of the previous life that was there in the rocks and in the sediment. And so I would love for us to find a stromatolite, and then we could look at it and we'd say, this is evidence of past microbial life on Mars. But and I think, if we don't find a stromatolite, then when things come back to Earth, I think there'll be very interesting investigations with mass spectrometers to really understand how Mars changed over time.
Okay. We hope you find a stromatolite for all.
Yes.
Yes.
We all hope we find a
We all
stromatolite.
find one. Next question, please. How has your faith been impacted by your experience of space exploration?
Well, I'm a person of faith, and have grown up as a person of faith. I've actually done different work overseas, teaching English and Bible, and I was in Peru, and we worked at a camp for homeless children. And so I find that helps me have the good perspective for the things I do. And I would say that by space exploration has impacted by faith by always encouraging me to think bigger about my God and not to limit who God is.
Yeah, good. And our final question. What is the next step for your career after this latest Mars mission, if we dare ask?
Yeah, well, it's a good question. My boss is asking me that too. A meeting this afternoon. I think my first answer is, I'm going to pause for a few months, take a breath. I've been working on this in the front office for many years. But of course, for me, I think this idea of sample return is just the capstone. It would be a great capstone to a career like mine, where I've worked on all the rovers. It's hard for me to go away from Mars. There's a lot of interesting stuff in astrophysics and everything at JPL, but Mars is kind of my first love. And so I expect it will be getting samples back from Mars.
Okay, thank you very much. I'm conscious of your time, and I'd like to close with this. Jennifer, there are people who do amazing things in space exploration, and we just read about their accomplishments in the media, but never have a chance to meet them. But every so often, a pioneer like you comes along who can relate her knowledge and experience not only to colleagues in STEM departments and universities, but also to colleagues in business schools. What you and your remarkable team do 140 million miles from Earth has as much to do with business management and leadership as it does with aerospace and astrobiology. On behalf of the Edinburgh Business School and Heriot University, thank you very much for joining us today. We wish you the very best. Thank you very much.
Thank you, David. It was a pleasure to be here.
Oh,
thank you.
Thank you very much.